Okay, so we're going to look at a problem on uniform circular motion, and it reads, this fall, my husband, kids, and I were visiting our hometown during Pacelli Panacea. It's a popular carnival-type event. At Panacea and many amusement parks, there is a popular ride where the floor of a rotating cylindrical room falls away, leaving the backs of the riders plastered against the wall. Suppose the radius of the room is 3.3 meters and the speed of the wall spinning is 10 meters per second when the floor falls away. Part 1. What is the source of the centripetal force acting on the riders? The source of that inward force acting on the riders. Explain your answer. Part B says how much centripetal force acts on a 55 kilogram rider. And part C says what is the minimum coefficient of static friction that must exist between a rider's back and the wall if the rider is to remain in place when the floor drops away. All right, so let's look at sort of what a top-down view of this looks like so we can at least understand what this ride looks like. So if I'm looking at a top-down view, the riders are all sort of standing, and let's just use the rider here. There's the top of their head. They're standing up, and I'm looking down on them, and we'll just say that the ride is spinning in that direction. So my object, my rider, is spinning in that direction. So the object that we're examining the forces on is the rider. Okay, so that's what we're interested in looking at. Now, let's draw a free body diagram of those forces and get a sense of what is the direction of that centripetal acceleration and therefore the direction of the force causing, net force, causing that centripetal acceleration, and then what's it due to? So before we even have to think about what type of motion we're dealing with, translational or circular, we can look at the forces acting on the object. So here's my rider acting, or my rider sitting there standing now. So now let's do a cross-sectional view. So here's the rider standing on the floor, and here's the wall of the ride. So we know the rider experiences a force of gravity, which is equal to mg. And just to think about those interactions, that force of gravity is between the rider and the earth. Okay. Well, the rider is got their back against the wall. Now, at the beginning of the ride, they're standing on the floor, but this isn't what we're talking about now. We're talking about when the floor's gone. So there's no standing on the floor, but they do have the back of their backs is interacting with the wall. So there is a normal force. It's just in this direction. So here's our normal force, and that's between the rider and the wall, okay? So leaning against that wall. Now, we know that that rider is not going to be moving up or down based on the way the problem is described, and that there's a frictional force. So if the floor fell away and the rider wasn't rotating, they would just slide down the wall. So there has to be a frictional force in this direction. Okay. Now, is it static friction or kinetic friction? Well, we know it's between the rider and the wall, and that rider isn't changing, it's not moving, so it's a static frictional force. All right, so those are our three forces acting on the rider. Now, if we know this object's moving in circular motion, it has a centripetal acceleration. We know that the centripetal acceleration always points towards the center. So we know that the centripetal acceleration, A sub c, points towards the center. So if we look at the object at this location, that's in this direction. So that is the direction of the centripetal acceleration. All right. Well, what forces, if we look at our free body diagram, what forces are in that direction? Well, the normal force. So remember, the forces causing the centripetal acceleration, what we call the centripetal force, which is a collection of forces, a net force that causes that object to move in a circle, is due to all the forces pointing in the direction of that centripetal acceleration. They're the cause of it. And so part A tells us that it's the normal force is the source of that centripetal acceleration, and therefore the centripetal force, the sum of the forces, but there's only one, so it's the normal force. All right, now it's asking how big is it? How big is that centripetal acceleration, and therefore that centripetal force? Well, if we do a force analysis, and let's just do it completely to see the whole visualization. We have 4 forces, horizontal and vertical. So force 1, 2, and 3. So force number 1 is not horizontal at all. The acceleration is along coordinate plane that we're used to, so we don't have to do any rotation. So that's 0, and we know that it acts down. There's my negative, and is equal to mg. Force number 2 is also vertical. That's our static friction, and we know that's equal to our coefficient times the normal force. The same, that n, remember, is between the same 2 objects. We've talked about that in past videos. And then our third force is the normal force, and in this case it's acting to the left. We'll just put that direction in explicitly. All right, so we sum our forces. They're equal to mass times acceleration horizontally, and the sum of the vertical forces are equal to mass times acceleration vertically. And now that we're solving motion with potential circular motion, we're adding a type of motion. We need to ask ourselves, am I moving translationally, or am I moving in uniform circular motion? We know we're moving in uniform circular motion, so which direction is that uniform circular motion in? Well, in our case, it's that horizontal plane. And so the sum of our forces are equal to the mass times the centripetal acceleration. The sum of that forces is our centripetal force, total centripetal force. So we'll bring that down. We have minus n is equal to the mass times the centripetal acceleration. This is part B. That centripetal force is whatever these values sum to. So the mass is, I've already forgotten, 55 kilograms times velocity squared over the radius. So we have 55. The velocity, it says, is 10 meters per second squared over a radius of 3.3 meters. So that normal force, that centripetal force, because that's the only thing acting, is 1,667 newtons, and we know it's acting in the negative direction. So the source of our circular motion, the source of our centripetal acceleration, the centripetal force, is 1,667 newtons, acting in the leftward direction. All right. The next question says, what's the minimum coefficient of static friction that must exist between a rider's back and the wall if the rider is to remain in place? Well, if the rider is to remain in place, then the sum of the vertical forces is equal to 0. So we have the frictional force minus the force of gravity has to equal 0. Well, we're told that the coefficient of friction, what's the minimum? We're trying to solve for the coefficient of friction. So we're going to solve for mu sub s. We'll bring mg to the over times n is equal to mg. So our coefficient of friction is the force of gravity, mg, divided by the normal force. Well, our normal force was the source of our centripetal force. So we know our centripetal force is 1,667 newtons. It's pointing to the left, but this is directional information. We've already considered direction. So we have the mass of 55 times g, which is 9.8, over 1,667. So our mu, our coefficient of friction, 55 times 9.8, divided by 1667 is equal to 0.32. All right. So recognizing that we're in a situation where we have circular motion, therefore that we have a net force that's causing a centripetal acceleration, and using the information to find that centripetal force based on that centripetal acceleration, and then to find that mu. Now I'm going to challenge you. I used this value in my solution to find the coefficient. But it turns out it's not dependent on the mass. Because we know that the coefficient of friction isn't dependent on the mass. So how is it that I don't need to know the mass of the rider to find that coefficient? What if I didn't give you the mass of the rider? Would we still be able to solve the problem? So I challenge you. The answer is yes, and I challenge you to sort of look at that perspective. All right, good job.